Okay, so it's 2 minutes past the hour, and hello everybody, and welcome to today's edition of the ENLA seminar, which will be the last one in 2020. So 2020 is finally coming to an end. This is Jörg Liesen from Berlin, and I'm wishing everybody a good afternoon, morning, or evening, wherever you are. It's a great pleasure for me to introduce today's speaker, Chen Greif from the University of British Columbia, where Chen is currently the head of the Department of Computer Science. Chen is very well known for his work in scientific computing and numerical linear algebra, and in particular, iterative solvers and preconditioning techniques for large and sparse linear systems. He has published numerous papers on these topics, and also he's the author of a very popular book, First Course in Numerical Methods, jointly with Uri Ascher. Also noteworthy, I think, jointly with Raymond Chen and Diane O'Leary, Chen edited and published Milestones in Matrix Computations, the selected works of Jean Golub in 2007. And let me particularly point out that this volume contains a biography of Jean written by Chen, which is based on many hours of interviews that Chen did with Jean in 2006. Chen is a very active member of our community, particularly in SciAm, where he served as the secretary and the chair of the Jean Golub SciAm Summer School Committee and several other leading roles. And before handing over to Chen, I would like to mention that, as usual, today, all participants in the seminar can ask questions during the talk, either in the Zoom Q&A or the YouTube chat. And these questions will be handled today by Melina Freitag and Daniel Kressner. And now, Chen, go ahead and please start with your talk on block-structured indefinite systems with rank-deficient blocks.
Thank you very much, Jörg, for the kind introduction, and it's great to be here. The commute was absolutely fantastic this morning. It didn't take me too long to get to the venue of the talk. So I'd like to start the talk just by dedicating this talk to the memory of a dear friend, Dominic Schetzau, who was a collaborator, and we've collaborated extensively. I'll be talking a little bit about things that we've done throughout the years, because my work with him has greatly influenced me in the last few years. And we lost him in July to a brain tumor that he fought against for many years, for about 15 years. And that's for you, Dominic. So the main topic here are saddle point matrices. And this is something that I've been interested in for many, many years. And I'm not alone in this. There's absolutely a huge activity. And that is because these systems are so popular. They really arise from problems with constraints. And that is very, very popular or common in numerical optimization, in the numerical solution of PDEs, and so on. And I'd like to talk today specifically about a certain setting of those problems, which I find very interesting, and it has some very unique mathematical properties. And I'd like to join me in being a little fascinated by those matrices to the extent you can. I'll try to convince you that they're interesting. Now, as I said, there's tons of activity. There are some wonderful surveys, and they keep coming out. There's a recent survey by Pearson and Pestana, which I find absolutely wonderful. They have a nice little feature of listing the citations in order rather than alphabetically, so you can kind of cluster everything you're interested in for a topic, which I find nice, but it's not the only thing that is very, very nice about this survey. It's just wonderful. There's a great book by Miro Rozlosnik that came out a couple of years ago, whose entire focus is saddle point systems. And there are many other surveys and books, all the way down to really classics at this point. And that's the book by Elman, Sylvester, and Wathen, and the survey by Benzi, Mikel, and Lisan. So all of these are wonderful sources for understanding a lot about saddle point systems, and in some cases beyond saddle point systems, but there's a lot about saddle point systems. Now, what I'm particularly interested in, this is really just the same matrix that I show in the little figure at the beginning. And I am going to focus on a particular rank structure. So let's just make sure that we understand notation, because I'm going to use that a little bit as we go throughout. So A is n by n, and I'm going to go back very quickly to that little thing, n by n, and n is large. And then B is m by n, and again, I'm going to irritate everybody's eyes, I apologize. So m by n, where m is a little smaller than m, or much smaller than n, and you have the zero block there. So this is really the structure. But what I'm particularly interested in is a situation where the nullity of A, which is just the dimension of the null space, is M, which means that the nullity of A is as large as the number of rows of B. The rank of A, as a result, is equal to n minus m. The rank of B is m because I'd like the matrix AB transpose B0 to be non-singular. And the kernels of A and B do not intersect except at 0. So these conditions allow for the matrix K, AB transpose B0, to be non-singular, while A has the lowest possible rank, n minus m. You decrease it by even one more, and it's impossible to have non-singularity. I think that's clear to everyone. But I think that it's important to spend a minute understanding that, because this is really what I'd like to talk about, and that is that n has a high rank deficiency. Now, this does come from applications. One application that I've been very interested in for many years now is the time harmonic Maxwell's equations with constant coefficients. Of course, also with non-constant coefficients, but it's much harder to perform analysis on that. And here, what is unique about this problem, first of all, it's not the only way to introduce this problem. There are many ways to do that. And in fact, P, the scalar, is a multiplier, as opposed to fluid dynamics, for example. Well, P has a physical meaning, it's pressure. Here, it's really a Lagrange multiplier. Some people even call it a dummy variable. And it could be added to the system to enhance stability. And there's some very interesting work about that that I will not touch upon. But the other very critical thing here is that the operator in front of U is curl. And curl has a very clean and beautiful null space and complete. And these are the gradients. So we know that curl of grad is equal to 0. And identically, and therefore gradient functions actually provide a very nice null space for you. And I think that everyone can appreciate that this again looks exactly like what I was talking about earlier. Curl has that large null space of gradients. And in fact, the rank of A upon discretization is n minus m. It depends on the discretization. This goes back to work that I did with Dominic a long time ago. And you use Nedelec elements or edge elements for U and nodal elements for P. And you can actually get that rank structure that I'm interested in. Another interesting thing that I'm just going to mention in passing, and then of course focus on an example, coupled PDEs. And in fact, there's some very, I think, increasing interest in multiple saddle point systems. There's a nice paper by Sogan and Zulaner recently that talks about true complement preconditioners, taking a function analysis approach. And this business of looking at things from a continuous point of view is also popular and important. I'm not necessarily going to focus on it at all in this talk. I just wanted to point out a few references here for this important way of dealing with those systems. So coupled PDEs are something that is very interesting for me, and we will stop at some point and then move to that in the later part of the talk. What I'm going to do is I'm going to describe some recent work that I did with Michael Wathen, and I should mention, I had it in the title slide, but just to make sure that I say it, Michael did his PhD with me until recently, and this work also describes joint work with another student, separate work with Ron Estrin. So my work with Ron and with Michael, two wonderful people to work with, is described in this talk. And the work with Michael focused on incompressible MHD, magnetohydrodynamics. This is a great example for two coupled PDEs. Each of them is of much interest. So what you can see here, and I think that everyone can see my little cursor here, this is Navier-Stokes. It's nonlinear, of course, and it really is Navier-Stokes. This is the Maxwell problem that I just mentioned. Here, R is the dummy variable or the Lagrange multiplier, and I changed what I used U earlier for B, so that U is the velocity. And these problems appear are of much interest in science. They basically model fluids of a certain kind, electrically conducive fluid. So just think of a fluid that is influenced by an electromagnetic field. And the important thing that makes this very difficult are those elements here. So these are nonlinear items. This guy here and this one here, and they're described here, you know, physically, Lorentz force and electromotive force, and they're hard. You can see that they're hard to deal with. They're nonlinear for one, and they also introduce skew symmetry into the system. Now, when kappa is large, then we might have serious problems here. This is where the coupling terms are really hard to deal with, and I will actually spend quite a bit of time talking about that later in my talk. So as I mentioned, I'm interested in rank-deficient blocks, and you know, these are problems that arise. I've already shown two. That was the time harmonic Maxwell and the incompressible magnetohydrodynamics problem. And there are many other problems that have that structure or a near structure. So there's no minimization with equality constraints, and it really depends on the number of constraints. You can generate artificially any rank you'd like for the leading block. That's quite straightforward. There are other problems that don't quite fit the bill, but are very interesting and relevant. For example, interior point methods have a small parameter, and near the solution, you have something that I wouldn't call a rank deficiency, but I'll call near rank deficiency. You start having very large and very small entries in your matrix. This is something that has been of interest to many people, including myself, in some work with Dominique Orban and Eric Molding. We try to understand the spectral properties of those problems. Valeria Simoncini has done some work with collaborators on interior point methods, and it kind of fits that bill to a certain degree. Vorticity or curl formulations of Stokes equations, again, give you that leading rank deficient block. There are geophysical inverse problems, especially if the sparsity is very high. then you can start thinking about a data matrix that is very, very highly rank deficient. And I apologize for this funny little term, highly rank deficient. It's kind of a negation. You can think of it as a very low rank or highly rank deficient. These are really the same. So I don't have much time to go over classical block preconditioning techniques, but I thought I would say one or two words about them. They've been introduced in many talks by many people that hopefully some of whom are listening to this talk. And you can find many references in the references that I mentioned much earlier. This is the sure complement, dual sure complement preconditioner. There is a famous result by Murphy, Golub, and Wathen that talks about the fact that there are only 3 eigenvalues. And these things are used as a starting point, very popular, especially for fluid dynamics. Constraint preconditioners, you do have, these are popular for constraint optimization because you work on the constraint manifold. You have a lambda is equal to 1 with algebraic multiplicity 2m, where m again is the number of rows of B, and geometric multiplicity m. These are non-diagonalizable preconditioned matrices. The third is something that I like to talk a lot about, not today, and this goes back again to my work with Dominique Schetzau. Some other people have done great work on this, early work of Powell and Sylvester on Ravia Thomas elements for Darcy equations. But basically what this is interesting in the sense that, again, if the rank of A is n minus m, if A has this maximal rank deficiency, then the preconditioned matrix, and I want to make sure it's clear, P sub A inverse K, where K is that saddle point system that I mentioned, would have precisely 2 eigenvalues, only 1 and minus 1. But that happens only if A is maximally rank deficient, if the nullity of A is equal to m. Only then would you have precisely 2 eigenvalues, and that is very, very useful. Of course, just like the first one here, you never form the sure complement here, you never form the primal sure complement here. You find an approximation, and that's something that I'll be talking about a little bit later on. And the thing that I'd like to talk about today, to focus on, are null-space approximate inverse preconditioners. This is work that started with Ron Esrin. I'm going to talk about it quite extensively in a few slides. And I just would like to give a bit of a heads up. This is an indefinite preconditioner of a saddle point form. And the C here is the null space of A. So it's interesting in the sense that you're using, instead of a sure complement, you use a null space. Now there, of course, is the famous law of preservation of difficulty. You will always have something difficult to deal with. And what I'm giving you, like maybe a sleazy salesperson, you know, I'm selling you the dream of don't use the sure complement, use instead the null space, which might not at all be easier to form, but sometimes it is available, as we saw for the Maxwell's equation. So here is a classical result by that is introduced. You can go back to the wonderful survey of Benzi, Golub, and Leeson, and that talks about the inverse of the matrices. And in fact, this is one of 2 results. And that is how the inverse looks. And I'd like to highlight here, of course, the inverse of the sure complement, the dual sure complement that we saw before. Here is a formula that is even more complicated, but it does not require the invertibility of the matrix A, just here, like here, and that could be advantageous. So the thing that I want to emphasize is here we're using this sure complement. That's a challenging matrix to form. And of course, you will only form sparse versions when you need to. And here you have the reduced Hessian, Z transpose A Z, where Z is the null space of B. So you can already see a couple of options here for the formulas of the inverse. Here is a theorem that now dives into the work that I've done with Ron Esrin. And here is an interesting result that can become handy for the rank-deficient situation. So again, I hope everybody is with me with regard to the notation. A is the leading block of that saddle point system, AB transpose B0. And what we're saying is the following. If you look at the inverse, then the rank of the trailing block that is denoted there by X, and remember that's an M by M block, the rank of it will be M minus R. And I want to just make sure that it's clear. The nullity of A could be anything between 0 and M, as we said before. I also mentioned that I'm interested in particular in nullity M. And now I'm saying that the rank of the trailing block is M minus R, where R is the nullity of A. So there's a very interesting corollary coming out of that. And that is that if R is equal to M, then M minus M is equal to 0, and the rank of X is equal to 0. So that's interesting. Why is that so interesting is because if the nullity of A is equal to M, as again I'm looking at, and again remember, for example, you have gradients of the curl satisfying that, then you have an interesting situation of an inverse of a matrix having a 0 block. And this is surprising, actually. This is something that is surprising in the context of this talk. You have a saddle point matrix that you start with. And what I'm saying is that if the rank of the original leading block, which is sparse, of course, if the rank is n minus m, or if the nullity is m, then you'll have a corresponding 0 block in that trailing position right here of size m by m. And we know how rare that is to find 0 blocks in an inverse of a matrix. So again, I want to emphasize that this comes up only when the nullity of A is equal to M. So here is a result from a few years ago that Ron and I found, and that actually generated some work following that of myself with Ron and later on with Michael, trying to make sense of this mathematical result. And this result, I'll let ourselves stare at it for a couple of minutes. Basically, it says that we now have a new formula for the inverse that uses the null space of A. So the matrix C satisfies AC is equal to 0. We assume again that null space of A is given and the nullity is M. And we have a matrix L there that is also associated with the matrix C, which is the null space of A, and with B, which is the 2-1 block of the saddle point system. So again, K is equal to AB transpose B0, and you now have a formula that does not have the dual Schur complement, does not have the reduced Hessian, but it does have a null space there. And it has a primal Schur complement that looks like that here. So basically, we have 3 formulas now, 2 that were mentioned in Benzi, Golob, and Listen, and 1 new formula that is mentioned here in the 3rd item. And it's based on the null space of A. It uses the primal Schur complement, as I said, and it assumes the null space of A is equal to M. And each of those may suggest a different block preconditioning approach. A few additional relations, and then I'll stop for a moment for questions. Again, all of this is related to the nullity of A is equal to M. You have a discrete Helmholtz decomposition that basically tells you that there's a direct sum of A the kernels of A and B gives you the entire space of Rn. That's quite obvious. It's really a discrete version of Helmholtz decomposition, and I think that that's something that is interesting and useful, but is quite intuitive. The second relation here is not at all intuitive, and in fact, it's an interesting personal story. When I worked with Dominik Schetzau back in 2006 and 7 on the Maxwell's equations, we noticed that if you choose W, the weight matrix, to be a scalar Laplacian, we actually prove that those two matrices are spectrally equivalent. That's all we could do. And it took another maybe decade of algebraic work to finally, and that's something that Ron and I have observed, that in fact you have equality, again, in the particular case of nullity of A is equal to N, between this augmented Schur complement and the weight matrix. That's very useful, in fact. And that's something that we use extensively to find the inverse. So the way I present this talk is not chronologically accurate. This result right here is based very strongly on those results that led to the result on the inverse. Relation of the null space of A to the primal Schur complement. This is something that I'll say later, but it's very, very important. C, which is the null space matrix of A, can be expressed in terms of A and B and this weight matrix W. And that's actually very important because that means that you do not need to find C explicitly directly by computing null space. And that's useful and important. And then a fourth relation that I have, which is interesting, is that if M and N are two matrices that are of size N by N, and they complement each other in terms of rank. So think of one as having rank N minus M, and the other have rank N, the M, then this relation right here is satisfied. And as a result, you can find an optimal choice for this parameter for augmented Lagrangian work. And that's something that has been of interest for many people. Benzi and Olshansky have an earlier paper in fluid dynamics. Patrick Farrell and collaborators have used that to develop very effective preconditioners, and so that is quite meaningful. Okay, I promised that I'll stop for questions, so maybe I will. For a moment here, and if there are questions, I'll take them. If not, I'll continue.
So on Zoom, there are currently no questions. YouTube, is anybody?
No questions on YouTube so far.
Okay. Thank you. So I'm going to continue. So this is the inverse that I mentioned earlier. And this is that preconditioner now, and the transition here is a little counter. It's not totally intuitive, but you can see here that if you approximate B transpose L inverse B by R, if you use the fact that AC is equal to 0, then you can get rid of this element. I'm not going to talk about that too much. I'm just saying that here is a proposed indefinite preconditioner that is based on an approximate inverse. And the next thing we do is basically we analyze that. So here is your approximate inverse. So again, I want to emphasize, you approximate this by some kind of a matrix. You dump this for good reasons because C transpose A is equal to 0. And then what you do is you get something that looks a little simpler. And now you do the usual thing, which is you analyze the eigenvalues of the preconditioned matrix, and you find that there's quite a large number. There's a nice clustering of eigenvalues, at least 2m of the eigenvalue 1, and you can even find the corresponding eigenvector. So that shows some promise. And interestingly, you can actually use the conjugate gradient method. And that's interesting by itself because it means that you take an indefinite matrix you precondition it with an indefinite matrix, and the result is a matrix that is that has a favorable spectral structure. And in fact, I'll show that structure here. That's quite interesting. So you take the Maxwell problem, indefinite, you hit it with an indefinite preconditioner that we just saw here, and the result is a matrix with eigenvalue mostly 1. Now, some work that I've done with Michael, which I don't necessarily have time to, well, I do call it a small digression. I'll just mention that this business of using conjugate gradient can be used also for block diagonal and block triangular preconditioners. You can just construct the Krylov subspace. A bit technical, I think I'll skip it and leave it at that. But just to mention that this is interesting in the sense that, again, you can use conjugate gradient. Of course, I don't want to sugarcoat. You know, there's that famous, joke about the mother who texts her son and says, "Start worrying, details will follow." And so let's start worrying, or maybe we're already worried. Tailored, this is all tailored for the specific case of nullity of A equal to M, and it's subject to availability. But I want to emphasize again, first of all, there are applications that fit this framework. I will mention that. I will talk about that next. We can simplify assumptions. I mentioned already that the matrix of the null space is available explicitly based on the matrices that are given. And there's an if-sup condition that basically says that your matrix R, the approximation, as long as it satisfies some kind of a relation on the null space of B, then the eigenvalues lambda of the preconditioned matrix are bounded away from 0. For those who deal with if-sup conditions with PDEs, this is just an algebraic version of that, and it's very, very useful. So I'm going to now pause for another second. And what I'm going to show now at the last part of my talk is some recent work with Michael that is related to that couple PDEs that I mentioned earlier, Incompressible Magnetohydrodynamics, and show how I can use this indefinite preconditioner. Any questions at this point, Melina or anybody?
You've just answered Daniel Schild's question, so you can go on. Nothing.
Thank you. Thank you, Daniel, for coming to my talk. So basically, there's a model problem here, coupled PDEs. And I mentioned already those two coupling terms. And we use some magic called finite elements. We use Taylor-Hood elements for the fluid terms and Nedelec nodal pair for the electromagnetic terms. And what we get is a system of nonlinear equations. The number of rows is mentioned here. And the coupling term is this guy here, C. And I do apologize for change of notation. C until now was used to denote the null space. I decided to leave C here just because it's faithful to the way we describe it in the paper. And I'll move to use G as the null space, and that makes sense because G is gradient functions. So this is how it looks, and this is how the linearized systems look. Okay, so you have the fluid dynamics here, you have the Maxwell here, you have a hard skew symmetric term here. This is a beautiful system, beautiful in the sense that it's not easy to solve. And you can partition it so that you feel more comfortable with the 2x2 thing, where K and S is Navier-Stokes, KC is the coupling, KM is Maxwell. Now there's tons of work on this, and I'm doing injustice to tens of articles that have appeared just recently, but I've listed here only a few that have influenced us quite significantly. Some great work, recent work by the second group mentioned here, monolithic multigrid, with some serious progress towards scalable solutions. And work that has greatly influenced our own thinking is the work mentioned in the first item here by those folks here, who do a wonderful job in their paper of trying to understand the discrete analog of these continuous hard, including the nonlinear term, and they derive block preconditioners. There's some work that we did, earlier work with block triangular, block diagonal preconditioners, and very recent work with Michael that talks about using that approximate inverse based thing that I talked about. So these slides are going to be a little technical. I'll try to go through them in a reasonable pace. There will be a couple of numerical experiments. First of all, again, these are a little hard to deal with, especially the coupling term. This is how it looks. And you have a few miracles here that help you. One miracle is that M is a curl, and C, if you remember, is a nonlinear term that looks like cross U cross B. So they share a null space. Those both are curls, and that is very, very useful here, okay? The other thing that we can see is that the Schur complement altogether of this matrix has a zero term as a result of that sharing the null space. This goes back to exactly that structure that I was talking about throughout my talk. When you have that maximal nullity, you will have a zero in the inverse, okay? So that is very, very nice, actually, and that's what you see here. Now, we know I always rattle my theoretical friends when I say an exact solution is a bad algorithm. And I think that in this audience, we know exactly what that means. So the inverse is intriguing in the sense that it has 0 blocks. Now, those blocks look small, but there are 0 blocks. There's actually 5 of them. There's this 0 block right here, which we expect because this is the entire premise of this talk. Look at this 0 and everything that I talked about. And then there are a few other 0 blocks that can be proven. And what we do is we approximate that inverse. And the important thing is to say that even though this is dense, it's actually much simplified and more 0 blocks. So we do need some computational gymnastics here. The inverse has 5 0 blocks. We have a whole arsenal of tools here. I mentioned the common null space of M and C transpose because both of them are curls. Therefore, you have a gradient function set as a null space. You can drop mesh-based block elements. You know, this is a PDE. You can actually look at all the mesh-related or mesh size-related terms and decide that some of those right here are small and can be dropped. You can use Sherman-Morrison to simplify inverses that appears there. You can use projection and null space properties. You can show that certain matrices that appear there are orthogonal projectors. You can use a nice property of the Maxwell's equations that shows that this augmented term is really equivalent to the mass matrix on the null space of the gradient operator. And you can do all kinds of things like that. And as a result, you can actually get that thing. As I mentioned, block matrices are not explicitly formed. There's a good degree of parallelism. And you can absolutely do a Schur complement block triangular preconditioner. It is cheaper per iteration, but for us, at least, it's less scalable. So again, all of these tools lead to what I showed here. A sparse approximate inverse. Not really sparse. I shouldn't use that term. It's not sparse. It's simplified and can be sparsely computed, if you know what I mean. And it has more 0 blocks. Okay, so this is a bit technical. You can actually find the eigenvalue, 1, the clustering of it. As I mentioned earlier and illustrated, you really have an indefinite matrix hitting another indefinite and non-symmetric matrix in this case. And all you can do is find the cluster of the eigenvalue 1. I will not dwell on it too much. These are numbers of rows that I mentioned much earlier, and I don't expect anyone to remember that. I just want people to understand the big picture, which is you have an eigenvalue 1 of a high algebraic multiplicity, and you can compute the corresponding eigenvectors explicitly. Here is an illustration that shows that, and it again goes back to the interesting fact that when you hit an indefinite, or in this case non-symmetric matrix, but you know, something that has the block structure with another thing that has the same structure that is very, very indefinite, then you can get real positive matrices. What you're seeing here is the real and the imaginary parts of the eigenvalues. Some of these eigenvalues are precisely 1, and I showed that right in this complicated theorem. And of course, this matrix is non-symmetric, so we would expect some of its eigenvalues to be complex, and you can see a little bit of that right here. But altogether, you see quite a nice clustering, and that will absolutely give you a good a good convergence rate. So let me show just 2 numerical experiments to wrap things up. This is a nonlinear problem, as I mentioned. You can use either Newton or Picard. Newton's method has a couple of additional terms, and in fact, it was impossible for us to perform the same type of analysis that Picard would give you. Picard is just more friendly for analysis. But it turns out that whatever observations that we've made analytically for Picard carry over in the experiment for Newton's method. The outer solver is preconditioned FGM-Res. And in exact solves, we basically took the best in the market, as we say, and you know, AMG from Hyper, you have the internal solvers, PCD, for example, for convection diffusion, the Hiptmeyer and Zhu preconditioner for the Maxwell magnetic problems, and all of those are done with inexact solves with tolerance 10 to the -1 or 10 to the -2. Michael did a fabulous work here, used Phoenix and wrote some serious code. And my role there was just to be a cheerleader, and we got some really, really good code out of that shows some nice results here. So here is a classic one, 3D cavity driven flow, and you can see the streamlines here just to illustrate. And one thing that I'd like to mention, I actually expressed that explicitly later. There's something called a Hartmann number here. It's a square root of 1,000. I'll get to that in just a minute and say what that is. But the thing that just needs to be remembered here is that if it's large, the problem is hard, in the sense that the coupling term, the skew symmetric coupling term is high, and that makes the problem harder. So here are the results. And again, this is where I did write Hartmann explicitly. It's the coupling term divided by the fluid viscosity and the magnetic viscosity. So as you can see, when the viscosities are small, then the Hartmann number is large, and that makes the problem harder. And what I'm showing here are just the nonlinear iterations. This was done using Newton. 4 iterations consistently. But the thing that is more encouraging is really that nice scalability for the outer FGM-Res iterations. Now, what I'm not showing here, just not to clutter the slide, are all the inner iterations, but all those are also scalable because we have very good solvers that I mentioned that have been tested and developed by other people and shown to be very effective. Here is another problem here. that's a Fichera corner. This is really an artificial problem. I don't know that this is, you know, so as opposed to the cavity problem, and we also have something called MHD generator that is used by many others and other physical problems. This is really just a three-dimensional version of an L-shaped domain, just to test the code on a non-smooth domain, of course. So you have singularity there at the corner, and we just constructed an artificial problem here. And again, what you can see with a fairly large Hartmann number, square root of 10 to the 5, you can see again a pretty good scalability. It's actually perfect. You have 4 or 5 nonlinear iterations, and you have approximately 28 iterations out there. The reason why, by the way, these are not integer numbers, the iterations, is just because we average over a variety of experiments. There's nothing flawed about that. The time is nicely scalable. The number of degrees of freedom goes all the way up to 5 million. And again, these just illustrate this. Okay, so I was instructed to give a talk of approximately 45 minutes. I think that I've accomplished that, and that will leave some time for questions. So what I wanted right now is just to summarize what we've seen. So first of all, I hope that I've convinced you that if you have a highly, I called it maximally rank deficient, or you can call it lowest rank block, that will still allow you to have non-singularity of the entire indefinite block, then you have some very unique algebraic or mathematical properties that you can only find in this case. And to list those, I'll say again, we looked at that augmented Schur complement version of, you know, you have a complicated Schur complement with a weight matrix that is simply equal to that weight matrix. You have a discrete Helmholtz decomposition. You have an explicit formula for the null space of your matrix A in terms of the matrices A and B and that weight matrix W, and you have a new formula for the inverse. So you can indeed, as I say in the second item, compute explicitly the null space. It offers an alternative to Schur complements. It's not necessarily an easier alternative, but sometimes it's available explicitly. And what you then can do is you can take that formula for the inverse, you can simplify it, and you can generate an indefinite approximate inverse preconditioner. It may prove effective. I've tried to illustrate that in the incompressible MHD problem by showing scalable results. And in addition to that, you have some interesting spectral structure there that basically says that if you hit that highly indefinite or non-symmetric matrix with something that really preserves those properties, then you have eigenvalues whose real part is positive and with a high level of clustering of the eigenvalue 1, and that's what makes the preconditioners tick. So with that, I'd like to end my talk. I'm going to put up a list of references here, and thank you very much. And I am happy to take questions.
Okay, thank you. Thank you very much, Chen, for the nice talk. We have one question at least. So Andy Woffen asks whether you've got any results for the case where the rank R is less than M. For example, M/2. So I don't know if you've got any particular application in mind. Yeah, that's the question.
Yeah, thanks very much, Andy. I do. So what I've done, one of the things that we have tried, I think Andy's question really goes back to that thing about limitations, the thing that I said that I'm not going to sugarcoat. So I am not going to sugarcoat it. I'm going to find it. So this is really the issue here, is that the entire thing is tailored for that. Nonetheless, to answer Andy's question, we have connected with Eldad Haber, who's given me, that's worked with Ron, an inverse problem with a very sparse data matrix. That's the matrix. The leading term is a sparse observation matrix. And what you can do when you do not have that rank, you can kind of either make up a complement that by, for example, an identity matrix or things of this sort, or just kind of declare some of the eigenvalues to be zero, even if they're not. And again, just generate an artificial basis. And at least for that problem, it works very well. I think that this is really an important question. How effective is it when you do not have that structure? And the answer is really that it's problem specific. My own work on interior point methods, which is not quite ready to be shown to the world, also illustrates that when you have small parameters, you can kind of ignore those small entries and try to just assume that these are zero eigenvalues. But the honest truth is that if you have n over 2, something that is very far, m over 2, then the analysis will not work and you will just have to resort to numerical experiments. And again, to emphasize, you can construct that matrix C algebraically with that formula that I showed, which is here. And so you always have a recipe to do that or to approximate it and just see what it gives you. And I think that's useful. I hope that answers the question.
Okay, thank you. I hope that answers the question too. Volker Mehrman says, great results, great application. And then we've got another question by Sriram Krishnan. Hopefully I'm pronouncing that right. I'm going to read it out. Will these preconditioners be applicable for higher order versions of these finite element methods? If not, what kind of problems would you expect?
Yeah, I think that's a great question. And I think that, so, you know, we have fairly, not very high, but we use Taylor-Hood for the fluid element. So it's a little higher than P1, Q0, for example. Then you don't need to worry about the trailing block there. And low order Nedelec elements. I will admit that we have not tried higher order finite elements. I have no reason to think that it would not work with a caveat. The work that we have done, those mixed or conforming finite elements, they have very clean properties. So for example, the null-space matrix of the gradients satisfies relations exactly, not approximately. And in some discretizations and maybe higher order finite elements, you might not have that beautiful properties. You might have something that is zero up to discretization error. And that could degrade the performance of that. So what you will need to do is to construct the higher element finite, sorry, the higher order finite element method in a way, or approaches in a way that mimics what we're doing here, which is very clean null space matrices, very clean relations, and that will guarantee analytically that you will be okay. If you only have it up to a discretization error, then again, you might have some, you know, some lack of cleanliness there. But again, you can use what I basically mentioned to Andy. You can still use those results. And I think that you have a good reason to expect that it will work, just like approximating a mass matrix for the Schur complement in fluid flow. You sometimes can do these things, and it works very well.
Okay, thank you. There was just one more question that came in, and I think we've got time to take this. So by Sen Chao, as the number of degrees of freedom increases, so does the CPU time. Can some steps in the calculation be parallelized? Thanks.
Absolutely. Thank you for that question. So yes, so this matrix is quite complicated. I mean, especially for the I'm going to the inverse. I did not show the inverse explicitly. It is a fairly ugly term, but the good news, I'm going to, sorry for going back to what I thought might be useful here. Let me not do that. Basically, you have the 4x4 inverse matrix. And when I mentioned that thing about computational gymnastics, maybe I'll go to that slide for a moment, right here. All of these things, so I mentioned here that there's a good degree of parallelism here. And that is correct because many of the quantities in that very complicated matrix repeat themselves. All these inverses that are there appear more than once, and you can actually solve in parallel. And that's actually a very nice thing about this matrix, which is otherwise quite complicated to look at. So I think that the answer is absolutely yes. You know, not everything can be parallelized, and you do have several solves per iterations, but you still have a good degree of parallelism.
Okay, thank you very much. I see there are no questions on YouTube, so I hand back to Jörg.
Okay, thank you, Melina, and thank you, Chen, for this great talk on one of my favorite topics. Let me just, okay, so I think if you stop your screen share, then I can pull up my slide. Okay, good. Thank you. So yeah, thank you, Chen, again. And I think in the name of the committee, I would like to thank all the speakers who have been following this seminar, or who have been presenting in this seminar, and this great audience who have been following everything since April. Remember, if there are some talks that you missed, they can be viewed on YouTube. So all the talks are taped and can be seen there on YouTube afterwards also. So the seminar series will continue in January of 2021. So that was our last talk for this year. We will continue on this bi-weekly schedule, Wednesdays at 4 p.m. The first talk will be given by Anne Greenbaum on January 13th, and then we have further confirmed speakers you can see here on the slide. The next one will be Nicolas Gilly on January 27th. Okay, so I think from everybody in the committee, although it's still some days, but this is the last seminar this year. Happy holidays, have a good start into 2021, and hopefully we'll see you then on January 13th for the first ENLA talk of 2021. So see you then. Bye-bye.